Hello, this is Mr. White, and this video is on the quotient rule. Take a moment, pause the video if you need to check out the 3 exercises that we're going to do here today. I'm going to launch right into that first one there. And we are asked to find h prime of x and h prime at that particular value, c equals 3 pi over 4. So before we jump into that, let's remind ourselves what the quotient rule states. So here is the quotient rule alongside the product rule. And the product rule I have displayed up here in the order that most textbooks will present it in, but you may recall that I suggest you get used to doing the product rule in this order. And since we've got addition going on here, I am allowed to just reverse the order. The technical way to justify that is to say that addition is commutative. But I am allowed to reverse the order. I cannot reverse the order in the quotient rule because that's subtraction, and subtraction is not commutative. So I trust you see now why I suggest you get used to doing the product rule in that order. It's because it more closely parallels the quotient rule. If you're used to doing g f prime first, well, that's the way it appears in the quotient rule, and it has to be that way in the quotient rule, g f prime. And if you're used to adding f g prime, well, it's not too big a switch to say, okay, with the quotient rule, I'm going to subtract f g prime. And of course, with the quotient rule, we've got g squared on the bottom as well. All right, so let me leave the quotient rule displayed up here, and I'm going to get rid of the product rule. We don't need it at this time. So leaving the quotient rule displayed here, let's go back to that exercise. And we have h of x is cosine x over 3x squared. All right, not really anything I need to do algebraically right off the bat. I'm going to jump right into the calculus. A lot of times it pays to do a little bit of algebraic cleanup first, but there really isn't anything we can do to that end for this problem. So the quotient rule is telling us to take the bottom function, to take the g of x, and multiply it times the derivative of the top function, f of x. So the bottom function in this case is 3x squared times the derivative of the top function, and the derivative of this top function is going to be negative sine x, minus the top function times the derivative of the bottom. So the top function in this case is cosine x times the derivative of this 3x squared, and that's going to be 6x. And that is all over the bottom function in parentheses squared. All right, I've done the calculus. That's all the calculus there is. The rest is just going to be algebra. So let's get rid of this calculus formula here and do some algebraic cleanup. Now I'm looking ahead. I'm experienced enough where I know to look ahead and see, are there any common factors here, here, and here? And I do see that there's a common factor. I trust you see it too, so let's be on the lookout for that. I could either try to factor it out right now, or I could go ahead and do something else first. I'm going to go ahead and do something else first. I'm going to go ahead and say that this numerator is negative 3x squared sine of x. I'm just simplifying this numerator there. Minus 6x cosine of x. It's customary to put the polynomial in front of the trig term when you're multiplying them. All over, now 3x squared in parentheses squared, be careful, do not put 3x to the 4th. That 3 is being squared as well, so we're going to put 9x to the 4th. Now again, if you had seen that common factor that I alluded to up front, you maybe could avoid this step, but I just figured since you're presumably rather new at this, I'll go ahead and do that extra step. Now I'm going to take care of that common factor. Now I'm going to factor out the greatest common factor of these 3 terms, and that would be a 3x, wouldn't it? So let's bring a 3x out from the top, and that's going to mean that inside the parentheses I need a, let's see, a negative x sine of x. And again, hopefully you're clear on that 3x times negative x sine x would give me this first term. And what's going to give me this second term? Well, that's going to be minus 2 cosine x. And that is all over I'm going to, again, take the 3x out of the denominator, which would leave me with 3x to the third here. All right, so that is our, and then of course I'll get rid of that 3x. I'll let them cancel each other out. And what I'm left with is h prime of x equals negative x sine x minus 2 cosine x all over 3x cubed. Now put a box around that because that is my h prime of x. So that's the general derivative that will work for any x value in the domain of the function. And now I'm going to focus on that particular value of 3 pi over 4. Okay, so let's scroll down, give myself a little room, and plug in 3 pi over 4. And again, this really isn't calculus anymore. This is just algebra. But it is some messy algebra, so it still may be beneficial to just kind of watch how I'm going to go through this. And you decide. You don't have to do everything exactly the way I do, but hopefully you may find some little techniques that you pick up and want to try out on your own. Now, this is where our unit circle comes in handy. I'm going to do negative 3 pi over 4. I just plugged in up there, and now I need to plug in the sine of 3 pi over 4. And we know from our unit circle skills that that is 1 over root 2. Minus 2 times the cosine of 3 pi over 4. And that's 1 over root 2 also, right? Wrong. It's negative 1 over root 2. See if you're paying attention, if you caught me on that one. All over 3 times quantity of 3 pi over 4 cubed. Now, I'm looking ahead a little bit. It's always good to look a step or two ahead. And I'm looking ahead and I'm seeing fractions within fractions. And even though I, Mr. White, am not always nitpicky about having rational denominators, I'm going to go ahead and choose to do a rational denominator. I'm looking at these root 2's here and thinking, you know what, instead of doing 1 over root 2, I could have done root 2 over 2 and negative root 2 over 2 for those two quantities, right? So I'm not insisting on this, but I'm going to choose to erase the 1 over root 2 and erase the negative 1 over root 2. And I'm going to just choose to put root 2 over 2. Again, I'm not saying you had to do that. I'm just choosing to. Part of what that allows me to do is it allows me to say, okay, well, this 2 now cancels out that 2. So there's a little benefit right there. Let's clean this up. We've got up here, we've got negative 3 pi root 2 all over 8. And now I've got minus negative root 2, right? So that's just plus root 2. But I'm anticipating, I'm looking a step ahead. So I'm going to put plus root 2, but I'm anticipating that I need to combine it with that first fraction. So why don't we go ahead and put 8 root 2 over 8, anticipating the next step of needing common denominators and all that stuff. And that is all over this denominator right here. And that denominator is going to be 3 times, now if I do 3 pi over 4, all cubed, all of those quantities are cubed, that's going to give me 27 pi cubed over 64. All right, I'm looking a step ahead and I'm thinking, okay, now I've got my common denominator up top. And I also see that I have a fraction within a fraction. So what if I did this? What if I did 8 over 8? And again, if you see a better way that you would like to handle these fractions, be my guest. This is just one of many ways we could do it. Okay, you probably heard I was a little interrupted there. I paused it for a moment. Okay, so why would I do that? Well, that's because this 8 up top will cancel out those 8s there. So again, fractions are not something you want to run away from in this class. Be comfortable with them, get used to them, ask for help if you need it. It's getting a little bit messy, so time to clean up a little bit here. Okay, where are we at? What we have up top is negative 3 pi root 2 plus 8 root 2. And that is all over this denominator. And let's see what I can do with that. Notice that this 8 will divide this 64 and give me an 8 down there. So 3 times 27 will give me 81 pi cubed. And that's all over 8. And now I could say, you know what? I've got a fraction within a fraction again. I'm going to pull that same trick again. I'm going to multiply by 8 over 8. And this 8 will cancel out that 8, and that will get rid of the fraction within a fraction, and we're almost there, folks. So I've now got, let me start with the easy thing first, the denominator, 81 pi cubed. I'm going to do one more thing with the numerator, and it's somewhat of a personal choice, but I'm looking at that numerator, and I'm looking at the root 2 here and here. I'd like to factor that out alongside the 8 here. So rather than distribute that 8, which one could do, and it wouldn't be wrong, but I'm going to factor out the root 2. And we'll start to appreciate in coming sections why it's often nice to have the derivatives in factored form. But I won't elaborate on that right now. I'm going to factor out the root 2 so that I have this 8 and a root 2 on the outside of some parentheses. And what am I going to have on the inside of parentheses? Well, negative 3 pi plus 8. All right, and I should point out that that negative 3 pi is going to be more negative than 8 is positive. So we're expecting that this is a negative quantity. Just thought I'd throw that out there. But you know what? I'm going to call it done. That was our h prime of 3 pi over 4. And now the moment of truth. Let's check via calculator and hope that we got it right, because if we didn't, we got some troubleshooting to do. All right, I've already entered in that expression in the calculator, and I see that my value is negative 0.00642-ish. And I've already entered in the function, the original h of x, into the calculator as well. I've got some window settings that I find work pretty well for this function. Notice that the y min and the y max are very tiny. That just took a little bit of tweaking to get for this particular function. But that gives me a nice display here. And when I go to second, calc, and then option number 6, I press the 6 button. And we wanted to evaluate at 3 pi over 4. I breathe a sigh of relief because that's the same number we had a moment ago. Negative 0.0064183, negative 0.0064183. So let's call this one done. All right, let's look at the second one. Find the derivative of the algebraic function g of x equals x cubed minus c cubed over x cubed plus c cubed. And it is generally understood in calculus that c is going to represent a constant. So we need to, even though it looks like a letter, it looks like a variable, we need to treat c as a constant and treat x as a variable. And one thing that I would like to just become a habit for you is to just think about what this function might look like, at least a little bit. Now, it would take more calculus techniques than we know at this time to really do a detailed analysis of what this function looks like without using a graphing calculator. But right off the bat, you should be able to determine where are the vertical asymptotes going to be. Isn't it pretty evident that if x equals negative c, that's where we're going to have a vertical asymptote? And isn't it pretty evident that the limit as x goes to infinity, it's not that long ago that we did limits going to infinity, that if we did the limit as x goes to infinity for this function g of x, ask yourself what happens as x gets really, really huge and c just stays constant. That's where the c's tend not to matter, and isn't that limit going to be just x cubed over x cubed, or 1? So think of what that tells us. That tells us that there's a horizontal asymptote. That tells us there's a horizontal asymptote at y equals 1. So again, with very little work, we already have a sense of what this might look like. Now let me go ahead and bring up a GeoGebra. Again, it would take more calculus techniques than we know at this time to do much further analysis there. But let me bring up the GeoGebra version of this function. And again, it's not a surprise that you see there in the dashed red lines, you see a vertical asymptote and a horizontal asymptote. The horizontal asymptote there is at y equals 1, and the vertical asymptote is at whatever the opposite of this c value is. And notice that I have c set to 2 right now, and therefore the vertical asymptote is at x equals negative 2. If I change the c value, which is one of the benefits of GeoGebra, it makes that very easy, I see that the vertical asymptote is now at negative 3. So we get a sense of what this function looks like. All right. let's go ahead and do some calculus on this now. One thing I might point out is that whatever our derivative turns out to be, do you notice that the derivative looks like it's going to be 0 when x equals 0? So whatever derivative we have, it looks like the slope of the tangent line right at the y-intercept there, right when x equals 0, is always going to be 0 no matter what I make c equal to. Okay, so let's clear that up and let's get into calculus. Find the derivative. Let's jump right into the quotient rule. So g prime of x, that's going to equal the bottom, x cubed plus c cubed, times the derivative of the top. And here's where you just need to slow down and remind yourself, x is the variable, c is the constant. So if I derive x cubed, I'm going to get 3x squared. But what do I get when I derive any constant, whether it's cubed or not? Any constant's derivative is going to be 0. So I just close the parentheses and move on. All right, so that was bottom times derivative of top minus top times derivative of bottom. Pause, take a look at the quotient rule formula if you need to make sure that this makes sense to you. So minus top times derivative of bottom. And again, same reasoning. Derivative of x cubed would be 3x squared. Derivative of this constant is going to be 0. And that is all over the bottom squared. X cubed plus c cubed. As always, make sure you don't get tempted to distribute this exponent in any way. That is not allowed. Now, should we FOIL out that denominator? No. Generally, I hope you're picking up by now, generally we leave the denominators in their factored, unfoiled form. Okay, so I could distribute out the top. There are a couple ways I could handle the top, and I'm going to choose the way that I like, although you may have a different way of approaching it. And I encourage you to try your way and see if we get the same answer. I'm going to notice that that 3x squared is something that I can essentially factor out. So let's take 3x squared, and let's put a big set of parentheses here. And inside that big set of parentheses, let's put the x cubed plus c cubed. And let's also put the x cubed minus the c cubed, but let's distribute that negative right there. So minus x cubed minus c cubed, I need to distribute the negative so it becomes a plus c cubed. And that's all over x cubed plus c cubed quantity squared. I notice that inside the big parentheses that the x cubed and the minus x cubed cancel out. So let's clear up a little room here and simplify. And believe it or not, we're almost done. That wasn't too bad. I've got 3x squared times c cubed plus another c cubed. That's 2c cubed, right? So 2c cubed times the 3x squared will give me 6x squared c cubed. All over x cubed plus c cubed squared. And again, that was our derivative. I want to come back to something I pointed out when we were looking at the GeoGebra file. Remember how I said that no matter what c is, remember how I said it looks like the derivative is going to be 0 whenever x equals 0? Well, we see that confirmed here. Whenever x is 0, whenever I take the derivative at 0, it doesn't matter what c is. My numerator is going to be 0 over some non-zero number there. Okay, so again, it's always good to have those expectations built in. And I'm going to call that done. If we wanted to, we could pick a certain c value, put it in our calculator, and check. And I'm going to leave that up to you, but I'm going to call it done as far as this example goes. All right, finally, complete this table without using the quotient rule. And we're given a bit of a gift here. We're told not to use the quotient rule. Here's what usually happens at this point in the course. Students have just used the quotient rule, and then every time they see a quotient, they have this knee-jerk reaction to use the quotient rule. Look, you could use the quotient rule on that. It would work, but it's not our best choice. Sometimes the quotient rule is absolutely necessary, but look closely at this one. It's not absolutely necessary here. We can do something with that algebraically. Let's rewrite it. Let's split that into two separate fractions. Let's split that into 13x to the 4th over 2x squared. minus 9 over 2x squared. And then simplify each term. That's going to be, see, 13 over 2, and then x to the fourth over x squared will give me another x squared, minus, and for the purposes of deriving, which is going to be our next step, I'm going to write this as 9/2 times x to the negative 2. Again, looking a step ahead, knowing that deriving is right around the corner. All right? So again, that was no calculus yet. That's still just algebra. That is still y right there. And now let's go ahead and differentiate. Instead of doing it in table form, I'll do it over here. Now I'll take the derivative and say y prime equals 13 over 2 times this exponent of 2 will just give me 13. And of course, this exponent gets reduced by 1, minus, and same deal here, I'm going to multiply that negative 2, and that's going to actually give me a plus 9x to the negative third. And if I want to observe that general rule of not having negative exponents, I'll do 13x plus 9 over x cubed. Now, should I combine that into one term? Should I give this a common denominator? I could. I'm going to somewhat arbitrarily just choose not to here. But again, beware when you look in the back of the book for odd answers. Maybe the book will do it, and I want you to resolve that for yourself and say, oh, that's the same thing. Okay? So I'm going to call that done. What would happen if you were to use the quotient rule on this? How much extra work would you be looking at? Well, I've already worked that out on the next slide. That same problem using the quotient rule would look like this. Not a tremendous amount of work, but certainly more than what we did on the previous slide. So notice that we do have the same final answer, 13x plus 9 over x cubed. Same answer, but again, even though we know the quotient rule and there are times where it's absolutely necessary, we've saved ourselves some time by not using the quotient rule here.